Welcome back. So in the previous video, we provided a general definition for mixing and talked about some of the factors that determine it. In particular, what we identified is that the rate at which mixing occurs is largely driven by this idea of a flux. Essentially, a flux is how fast is a quantity per unit volume crossing over a plane into a different region of the fluid. But what we haven't done yet is identified what the processes are within a flow that actually create these fluxes. Essentially, what is causing fluid within region 0 to cross this plane into region 1. And there are a couple of the most common methods for this to happen, which is what we're going to describe now. The first of which is at the microscale level. So this is looking at the behavior of individual molecules within the flow. And this is a concept known as molecular diffusion, the topic of this video. And then next, what we'll look at is more at the macroscale. So zooming out and looking at the behavior of the overall fluid and identifying something that's known as turbulent advection. Molecular diffusion is based on the net movement of molecules that's corresponding to random motions known as Brownian motion. So from previous chemistry lessons, you may have learned that all molecules have some movement associated with it. This movement is closely corresponding to heat or temperature. And based on this movement and collision with nearby molecules, you can have that an individual molecule might eventually slowly travel from one location to another location at the microscopic level. And so if you consider these individual molecules, in addition to an existing concentration difference, so a series of red molecules on top of a series of gray molecules, very slowly over time, this random Brownian motion is going to cause the movement of the high concentration of red to move into the region where it didn't previously exist. So this change in the concentration difference due to Brownian motion is known as molecular diffusion. How you define this diffusion mathematically is independent of exactly what quantity x you're talking about. It's always going to be proportional to the gradient using this definition that I'm giving here. So the flux is equal to the negative of some constant multiplied by the gradient in that quantity over space. And this diffusivity constant is what quantifies the direct relationship between the gradient and the flux itself. Again, as I noted, this is the same regardless of what the quantity x is. However, the exact constant that you get and the exact name for this equation is different for different quantities like momentum, concentration, and heat. The first law I'd like to discuss is Newton's law of viscosity. So the center and the right-hand side of this equation represent Newton's law, where the shear stress is equal to the gradient in the velocity multiplied by the viscosity. And this can be directly related to what is known as the momentum flux. This relation, how you get from Newton's law to a momentum flux, is a little bit tricky. I'll try my best to understand the concept, but it may be something that's still difficult to wrap your head around. So Newton's law gives us that if you have some sort of a difference in velocity across a plane, the resistance of the flow across that plane to this difference in velocity is going to be related to the dynamic viscosity, which is the density times the kinematic viscosity. And this is acting in the direction opposite to which the flow is going. Now, at the same time, this shear stress is directly related to how fast that difference in velocity between u0 and u1 is disappearing due to the movement of momentum from region 0 to region 1. And so even though they're in opposite directions, you can get a clean mathematical connection between this flow resistance and how fast the flow momentum is moving across the plane. The second law is Fick's first law of diffusion, which corresponds to concentration flux. So this looks exactly like the equations we saw on the previous slide, and you can see a clear connection between the top and the middle one, where you have some sort of a diffusivity constant, and then you have how that average quantity is changing across the direction of interest, which for our cases is depth. And then finally, we have Fourier's law of conduction, which relates to the flux of heat. So the heat flux is equal to some diffusivity constant for heat and the way in which the average temperature is varying across space. The rate of molecular diffusion, which is again a microscale process, is very slow once you zoom out to the macroscale and look at overall differences in the fluid. And you can see an example of this in the animation here at the bottom, which again is coming from National Committee for Fluid Mechanics, where you initially have a concentration difference in dye with a high concentration and low concentration region respectively, and the rate at which this difference is disappearing is very, very slow, on the order of weeks and longer, if the only mechanism that is present is this microscale molecular diffusion. This very slow diffusion is represented by very small diffusivity constants in the equations that we showed on the previous slide. So the kinematic viscosity, nu, representing the connection between the velocity gradient and the momentum flux, is on the order of 10 to the minus 6 for water. The diffusivity constant for concentration is on the order of 10 to the minus 9 when it's a concentration of anything in water. And for heat, it's typically on the order of 10 to the minus 7 for water. So these variables and their values depend on what specific quantity you're talking about, momentum, concentration, or heat, but the units themselves do not differ between these three examples. And in each case, it's meters squared per second. The reason why they don't change is because each of them is generally representing the same thing: how you connect the gradient of a quantity with the flux of that same exact quantity. And what we're going to do next is look into some of the macroscale processes and see how their diffusivities compare to the microscale.